Hello students, this is your chemistry teacher. Today we are gonna discuss the chemistry of group 18 elements. So these are the contents today we will be discussing on. The first of all, introduction, occurrence and atomic radius of group 18 elements. Secondly, variation of electron gain enthalpy and cause of inertness of the group 18 elements. Thirdly, fluorides of xenon, their preparation and properties. Fourthly, structure of xenon fluorides, and at the last, structures of HCF6 and use of noble gases. So let's get started. So first of all, uh, the group 18 elements include helium, neon, argon, krypton, xenon and radon. These are the elements present in group 18, and these elements are called noble gases or inert gases. Why are they called noble gases or inert gases? Because if we see the electronic configuration of those elements, we will see that electronic configuration is going to be ns2 np6. So we can see that it is a stable completely filled cell. Okay, so as the valence orbitals are completely filled, they are not going to react with anyone. Under certain conditions, they might react with certain elements to give some products, but in normal conditions, they are very inert to react to anyone. Okay, now let's discuss the occurrence of the elements. So except radon, all the group 18 elements occur in atmosphere. Helium, neon, argon, krypton, xenon, these are all present in atmosphere except radon, because radon is a radioactive element. Okay, helium and neon are found in pitchblende. Pitchblende is a mineral. Pitchblende is a radioactive mineral. Okay, so helium and neon could be found in the radioactive mineral pitchblende. Radon is a radioactive element. So this is basically radon is basically obtained as a decay product of radium. This is the reaction that you can see over here, that radium 88 to 26, this is the isotope of radium that is dissociating into radon 86 to 22 with the liberation of alpha particle. Okay, now what are the atomic radius going to be for these elements? So atomic radius increases from helium to radon from top to bottom. As we move from top to bottom from helium to radon, the atomic radii continuously increases. Okay, moreover, one thing is very important to observe here, that noble gases have a higher atomic radius than group 17 elements. What our general expectation is, like when we move from left to right, the atomic radii decreases, right? So according following that trend, uh, group 18 elements are supposed to be are supposed to contain more atomic radius, or uh, uh, are supposed to have more atomic radii than group 17 elements, but actually group 18 elements have the atomic radii larger than group 17. So this is anomalous behavior. So this anomalous behavior is due to completely filled cell that is present in the valence shell configurations of noble gases. We know valence shell configuration of noble gases is ns2 np6, right? So here, as you can see, that the orbitals are fully packed. All the s and p orbitals are fully packed, and due to this reason, the electron cloud will be expanded to a extent, a little extent, in order to avoid the inter-electronic repulsion, because s and p orbitals in the configuration, you can see that s and p orbitals are fully packed with electrons. So to avoid the inter-electronic repulsion, the radius will be expanded to some extent, and for this reason, due to this expansion of the radius, or due to this expansion of the electron cloud, uh, noble gases uh, noble gases will have greater atomic radius than group 17 elements. Okay, now let's move on to the variation of electron gain enthalpy and cause of inertness. What is the cause of inertness of these elements? So what is the variation of electron gain enthalpy? So since they have the completely filled cell, the tendency to accept electron, hence electron gain enthalpy is taken to be zero. This is a very important point, as we have already discussed that electron gain, the valence shell configuration of group 18 elements are, valence shell configuration is ns2 np6. So there is no vacant orbital available to accept, or to accept electrons from other elements, and that's why they are very much reluctant to react with other elements, or to react with other species to react with other species, and that's why the tendency to accept electron is very much less. Rather, we can say the tendency to accept electron for these group 18 elements is taken to be 0. Okay, that's why electron gain enthalpy of these elements are taken to be 0. Okay, now for some elements, positive electron gain enthalpy, that means the delta H Eg, this value, sometimes the value of the value of delta H Eg is found to be positive. Okay, so it is only possible if only under drastic condition, or only under if we give high temperature to those elements, then only some electrons could be fit into the atoms. And for this reason, some elements of this group 18 can show the positive electron gain enthalpy, but this is a very rare case. And if you give a high amount of energy, very high amount of energy to these elements, then only they can show positive electron gain enthalpy. Otherwise, they in general they exhibit uh, electron gain enthalpy, zero electron gain enthalpy, or their electron gain enthalpy is taken to be 0. Now, what are the reasons for which they show the inertness, they show the reluctancy to react with some other substances? Okay, we know that noble gases are not going to are very much reluctant to react with someone, or to react with other chemical species. The noble gases are very inert in nature. What is the reason behind it? The reasons are: number one, they have completely filled outermost shell, that is ns2np6. For this reason, there is no tendency to accept or reject electrons from the valence shell, and that's why they are very inert. They do not react with anyone in any condition. Secondly, they have electron gain enthalpy 0, that means they have no tendency to accept electron in their valence shell, and that's why no reaction is possible for these group 18 elements. And thirdly, very high ionization energy, since they have the completely filled outermost shell ns2np6, so, and that is a very stable, very stable configuration, and that's why they high amount of energy is needed to take out one electron from this outermost shell, and for this reason they possess high ionization energy. And due to these reasons, like high ionization energy, zero electron gain enthalpy, and completely filled outermost shell, they are very inert in nature. Okay, now let's move on to the fluorides of xenon, their preparation and properties. So first of all, what are the preparatory method for the generation of for the preparation of these fluorides of xenon? So xenon mainly react with F2 at high temperature to give three binary fluorides. What are they? They are XeF2, XeF4, and XeF6. Xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. How are they gonna prepared? They are prepared by these processes. Like xenon is reacting with, in the first process, xenon is reacting with fluorine at a temperature range 650 Kelvin, pressure 1 bar, to give XeF2, xenon difluoride, and this xenon difluoride is solid in nature. In the second process, as you can see, that xenon is reacting with two molecules of fluorine in the temperature 800 Kelvin and pressure 7 bar to give XeF4. In the third process, xenon is reacting with 3 moles of fluorine to give you xenon hexafluoride at the temperature 580 Kelvin and pressure 70 bar. So what are the properties of these compounds? So mainly xenon fluorides, these xenon fluorides that are prepared in this process, they are hydrolyzed to give xenon oxofluoride. Hydrolyzed means basically reaction with water. So in the first process, that you can see that XeF6, xenon hexafluoride, is reacting with water to give xenon trioxide with the liberation of HF, hydrofluoric acid. So in other way, it can react with water, like XeF6 can react with water to give you XeOF4. It's oxofluoride, xenon oxofluoride, XeOF4. Later on we will be discussing on these on the structure of these compounds. Okay, now in the third process, you can see that XeF6 is hydrolyzed with water, or is reacting with water to give you XeO2F2 with the liberation of HF. Okay, now one thing is important to observe here, that in this hydrolysis process, these three processes are hydrolysis process. Hydrolysis of whom? Hydrolysis of XeF6, xenon hexafluoride. So in the hydrolysis process, the oxidation state of xenon is not going to be changed. in any of this process. Here in the first process, as you can see, that xenon has the oxidation state -6. So here also in XeO3 the xenon has the oxidation state -6. So in each of these process, if you look on this process, you will found that there is no change of oxidation state of central xenon atom in this process. Here also it is -6, here also it is xenon has the oxidation state -6 in this compound also. Here also it is -6, and here in this compound XeO2F2, xenon has the oxidation state -6. Okay, so in the hydrolysis reaction, one thing is very important to observe here. In any hydrolysis reaction, the central atom or in the main compound, the central atom will not gonna change its oxidation state. That means we can conclude one thing from this hydrolysis reaction, that whenever XCF6 will be participated in the hydrolysis reactions, then there will be no change in oxidation state of central xenon atom. And since there is no change of oxidation state of central xenon atom, we can say that these reactions are not the redox reactions, because redox reactions are those reactions where there occurs a change in oxidation state of some elements, right? So here xenon is not going the oxidation state of xenon is not going to be changed either in the reactant compound or in the product compound. Either in the reactant compound or in the product compound, xenon oxidation state is same for both the reactant and product, and that's why we cannot say these reactions as redox reactions. These are normal hydrolysis reactions where xenon oxidation state of xenon is not going to be changed. It remains same in reactant and also in products. Okay, now secondly, xenon fluoride can bind with some compounds which can accept fluoride ion, or which can accept electron pair in the which can accept electron pair. Okay, like PF5 phosphorus pentafluoride, SBF5 antimony pentafluoride. These are the compounds that can accept fluoride ion, or these are the compounds that can accept electron pair or lone pair. Okay, as you can see over here, that xenon tetrafluoride XeF4 is reacting with SbF5, and this species is formed. This species XeF3 plus and SbF6 minus is forming. Now what is happening behind in this reaction? Actually, the one fluoride ion from XeF4 is actually transferring actually transferred from XeF4 to SbF5. As you can see that if one fluoride ion is eliminated from this XeF4, it is going to be XeF3 plus, and if the fluoride ion is added up in this compound SbF5 is going to be SbF6 minus. So this is mainly the transfer of fluoride ion from XeF4 to SbF5. Why is it happening? Because SbF5 is a good fluoride ion acceptor. Okay, now one thing is important to observe here, that whenever XeF6 molecule or xenon hexafluoride reacts with metal fluoride, okay, then the same type of reactions occur like the second reaction, like the reaction properties number 2. Okay, so here also metal fluoride means what? Metal is positively charged M plus, and fluoride ion is negatively charged F minus. So here also XeF6, now XeF6 is going to accept the fluoride ion from metal fluoride, and the species that are going to be formed are XeF7 minus. That means one fluoride ion from metal fluoride F minus is transferred from MF to XeF6. So XeF6 is going to take up that fluoride ion and it will form XeF7 minus, and at the same time MF will reject the fluoride ion and it will be M plus, or it will be M plus, where M stands for any metal like sodium, potassium, etc. Okay, now let's move on to the structures of xenon fluorides on the basis of VSEPR theory. So we have already discussed this kind of structures in group 17 elements. Okay, now in the first compound, as you can see, it is a XeF2 molecule. So here the central xenon is going to have 8 electrons. It is forming 2 single bonds, so plus 2 electrons, total 10 electrons. 10 electrons means 5 electron pair. So 5 electron pairs means structure should have been trigonal bipyramidal, but among this 5 electron pair, 3 are lone pair that are present in the equatorial plane, as you can see in the structure, and 2 are bond pair. These are the 2 bond pairs. So as we know that lone pairs are not going to contribute in the main structure. Okay, so the structure should have been trigonal bipyramidal, but actual structure is linear. Okay, or you can see or you can say that the geometry of this molecule is trigonal bipyramidal, but the structure is linear because lone pairs are not going to contribute in the main structure in the determination of the structure. Okay, now in the second structure, that is the structure of XCF4 molecule, where central xenon will have 8 electrons plus 4 bonds. It is making 4 bonds, so plus 4 electrons, total 12. So total 12 electrons. So 12 electrons means 6 electron pairs. So as we know, the if there are 6 electron pairs, the structure should have been octahedral, but among these 6 electron pair, 4 are bond pair and 2 are lone pair that are present in the axial positions. Okay, the structure should have been octahedral, but due to the presence of 2 lone pair, and as we know that the lone pairs are not going to contribute in the main structure, so the actual structure will be square planar. Okay, now let's move on to the third structure. In the third structure, xenon is the central atom, so it will have 8 electrons. It is making 3 sigma bonds. In the structure, 3 sigma bonds are there, so plus 3, and at the same time it is making 3 pi bonds with oxygen atom, so plus 3 again, with 3, due to the formation of 3 pi bonds. Okay, now as this compound contains 3 pi bonds, and as we know that pi electrons are not going to contribute in the main structure in the structure determination, so we have to exclude the pi electrons from the total electron count. So we have to exclude 6 electrons because there are 3 pi bonds, so total 6 electrons we have to exclude from the total electron count. So there will be overall 8 electrons. 8 electrons means 4 electron pair, so 4 electron pair means structure should have been tetrahedral, but among these 4 electron pair, 3 are bond pair and 1 is lone pair, and this lone pair is not going to contribute in the main structure, so the structure would be pyramidal. Now let's move on to the fourth structure, where xenon is the central atom, so it will have 8 electrons. It is making 4 bonds with 4 fluorine atom, so plus 4, and it is making double bond with oxygen atom. So among these two bonds, one is sigma bond, so plus 1 for one sigma bond and plus 1 for one pi bond, but we have to again exclude the pi electrons from the total electron count. So minus 2, we have to exclude these 2 electrons of the pi bonds. One pi bond is there, so 2 electrons we have to exclude. These are the 2 pi electrons that we are excluding from the total electron count. Now there will be 12 electrons. 12 electrons means 6 electron pair, so so structure should have been octahedral, but there is a lone pair among these 6 electron pair, so there are total 5 bond pair and 1 lone pair, so structure would be square pyramidal due to the presence of this lone pair, and this lone pair is not going to contribute in the main structure. So structure should have been octahedral, but due to the presence of this lone pair, the structure would be square pyramidal. Now let's move on to the structure of xenon hexafluoride. It has a octahedral structure. The determination of the octahedral structure is again based on VSEPR theory, where xenon is the central atom and it is making 6 covalent bonds or 6 bonds, sigma bonds with 6 fluorine atoms, so plus 6, total 14 electrons. 14 electrons means 7 electron pair. So among the 7 electron pairs, 6 are bond pair, as you can see over here in the structure. 6 are bond pairs and 1 is lone pair. Now the most important fact is that this lone pair is continuously changing its position in the following way, as I have demonstrated here in this picture. So this lone pair, the lone pair is called stereoactive lone pair, that we will be discussing on later on in the further topics of class 12. So this lone pair is continuously changing its position throughout this octahedral structure, and for this reason this is not a perfect octahedral structure. So thus, due to the presence of this mobile, you can say mobile lone pair, that is continuously changing its position throughout the octahedron, so due to the presence of this type of lone pair, the structure is bit distorted, and that's why the structure is called distorted octahedral. Now what are the uses of this noble gas? Mainly helium. Helium is used in driving apparatus, and also neon is also used in some discharge tubes. So these are the main uses of noble gases, especially helium and neon. Okay, so these are the topics that are the most important topics of group 18. Hope you have understood all the topics. See you in the next class. Thank you.